Assalamu alaikum. So I gave you homework problem at the end of the last class that was about quantum teleportation. Was anyone able to do that problem? Anyone? I thought we should save some time today. All right. So today is going to be our last class in this module of quantum physics. In the next class, hopefully, we're going to start with a more physical picture. We're going to look at the equation of motion for quantum systems. Today's class, I hope, is going to be interesting. We've already looked at all the tools of the trade. We've collected all the arsenal. We have all the machinery in front of us. We know what states are. We know what transformations are. Now we're going to look at some applications. We also know what entangled states are. So one of the applications that we're going to look at today is quantum teleportation. First of all, let me draw the circuit because it's easier to explain teleportation through a quantum circuit. In quantum teleportation, the basic idea is that if we have a qubit, arbitrary qubit, in an arbitrary state, any state whatsoever, and I can write the general state of a qubit as A ket 0 plus B ket 1. Now the task of teleportation is, excuse me, please pay attention. The task of teleportation is to transfer this quantum state to another physical particle. And we already know that cloning is not allowed. So we cannot copy the state. So we have to transfer the state while respecting the no cloning restraint. So how quantum teleportation works is as follows. There is a qubit that one wishes to teleport. And then in addition to that qubit, there are additional 2 qubits. These 2 qubits are entangled with one another. So they could be in a Bell state, ket phi plus. And let me reiterate what ket phi plus means. Ket phi plus is 1 over under root 2 ket 0 0 plus 1 1. This is an entangled Bell state for 2 qubits. For completeness, let me write all the 4 Bell states. The second Bell state is phi, capital Phi with a minus sign, 1 over under root 2 ket 0 0 minus 1 1. The third ket state, Bell state, could be psi plus 1 over under root 2 ket 0 1 plus ket 1 0. And the fourth kind of Bell state is 1 over under root 2 ket 0 1 minus 1 0. Excuse me, there's some constant hum in the class which is disturbing. So these are the 4 Bell states. Now what we would like to do is we would like to teleport this quantum state, which means we would like to transport this quantum state, the information carried inside this quantum state to another qubit without physically moving matter. So how do we do that? We correlate this qubit with an additional pair of qubits, and those 2 qubits are entangled, they're in the Bell state. 2 of the qubits go to Alice's world. So this is Alice's world here. Alice lives in this universe. And the third qubit goes to Bob. Bob could be really far away in space, in the universe. some other planet, on another part of the earth, so on. So this is Bob's world here. Bob lives here. So two qubits are produced. They are produced by a source. They are entangled. One of the qubit is passed on to Alice and the second qubit goes to Bob. And Alice is now in possession of two qubits. One qubit is the quantum state that she wishes to teleport, and the other qubit is one of the entangled pair, and she does a quantum operation which is a controlled NOT gate on the second qubit dependent on the first qubit, followed by a Hadamard gate on the first qubit. So this is her operation. Nothing happens to Bob's qubit. Bob's qubit remains in whatever state it started off with. So this is the kind of sequence of events that is taking place. Now Alice performs these unitary operations on her qubits. Now I would like you to tell me what state is achieved at this particular point. Remember, it's a 3 qubit problem now. We have 3 qubits. So we really have to respect the dimensionality of the system. We really have to talk about 3 qubits. We cannot talk about just the first qubit or just the second qubit or just the third qubit or just 2 of the 3 qubits. We have to talk about all 3 of them together because it's a correlated state, and it's a very strong correlation between 2 qubits. It's entanglement. So would you kind of follow the argument with me and see how this quantum state progresses with time? My initial input quantum state, my psi in, of course the first qubit is A ket 0 plus B ket 1. This is my first qubit, correct? The second and third qubit are in an entangled state. All right, so this is what I start off with. Now it's quite easy to, and it's going to be convenient if I kind of expand this. First qubit, second and third qubit, and there's a tensor product. The tensor product is not normal multiplication, by the way, you already know that. So what I would like to do now is I would write this as a giant superposition. A ket 0 tensor product with all of this, that would give me 0 0 0 plus A 0 1 1 plus B 1 0 0 plus B 1 1 1, and there was a 1 over under root 2 here, so this becomes 1/2. So this is my input quantum state. Now we would like to calculate the quantum state as it exists after the first control NOT gate. So after the first control NOT gate, the state evolves. So the first control NOT gate, which is a gate between 1 and 2, the first and the second qubit. Now what does the control NOT do? Control NOT inverts the target qubit if the control qubit is in the state 1. And this controlled NOT gate is doing nothing to the third qubit. Got it? So can you just spell out what's going to happen here? 1/2 A ket 0 0 plus A 0 1 1 plus B 1 1 0. Nothing happens to the third qubit. Only the second qubit gets inverted if the first qubit is in a state 1, and the last term here is 1 0 1. So this is what the quantum state progresses into after the first control NOT gate. Now let's see what happens after the Hadamard gate on just the first qubit. This is an example of a genuine 2 qubit gate. Now the system sees a 1 qubit gate just on Alice's first qubit. Yes, please.
In the in state.
In the in state, yeah.
In the in state, don't we have to write the 5 plus twice because the second and third qubit are both in that state?
So so this is the second and the third qubit. So this is a 2 qubit state. This is the first qubit in the entangled pair. This is the second qubit in the entangled pair, right? So this encompasses, this is a 2 qubit state. It's a multipartite state already. Nice that you asked this question. Now we would like to see what happens when a Hadamard gate is applied on just the first qubit. Hadamard gate on the first qubit only. 1/2, let's put a big brackets A. Now nothing happens to the second and the third qubit. The first qubit goes into a superposition. If the first qubit is ket 0, it goes to ket 0 plus ket 1 with an under root 2. And I just bring that under root 2 out of this big factor here. Then I'm left with, now I need to write down the identity of the second and the third qubits. I cannot ignore the second and the third qubits. So the second and the third qubits remain unchanged like this. Then the second term with an A also gets into ket 0 plus ket 1, ket 1 1 plus B. Now what do I write over here for the third term? Ket 0 minus ket 1 tensored with 1 0 plus B ket 0 minus 1 tensored with 0 1. Now it's going to be convenient if I going to expand all of this. So this gets to 1 over 2 under root 2 A 0 0 0 plus A 1 0 0 plus A 0 1 1 plus A 1 1 1 plus B ket 0 1 0 minus B ket 1 1 0 plus B ket 0 0 1 minus B 1 0 1. So this is my overall state. Now what I would like to do, something really interesting happens here. Alice's computation stops here. Now she measures her first qubit and the second qubit. She measures both qubits in her possession. How does she measure? She might have a beam splitter that has a ket 0 channel and a ket 1 channel on each of the qubits, and she places detectors in front of this. So the first qubit can either come out as ket 0 or ket 1, and the second qubit could come out as ket 0 or ket 1. Got it? So how many possibilities for these outputs do we have? How many possibilities exist? 8. We're not looking at the third qubit. We have 4 possibilities. What are those 4 possibilities? 0 0, 0 1, 1 0, 1 1. So this could be 0 and this could be 0. This is the first possibility. The second possibility is that this could be 0 and this could be 1. The third possibility is that Alice could get 1 on the first qubit and 0 on the second qubit, or Alice could get 1 on both of her qubits. So now she does a measurement of her 2 qubits. Now if we were to do a measurement, we would like to find out the probabilities of all of these possible outputs. Now how do I do that? So I just take this term 1 over 2 under root 2, and now I do a cunning kind of scanning of this superposition, and I and I scan this superposition in the following fashion. I look at the first 2 qubits. You just look at the first 2 qubits and see which terms have a 0 and a 0. First qubit 0, second qubit 0. So I get, how many terms would I get with this configuration? 2. I get this term and I get this term. So is it possible to factorize out the state of the first and the second qubit and separate it out from the third qubit? Yes, I can do that. So I just take the terms that I've highlighted with the blue triangle and factorize out the state of the first 2 qubits with Alice and write down what remains as the identity of the third qubit Bob possesses. Alice doesn't possess the third qubit, remember that. Bob has the third qubit. So this is before a measurement takes place. So what should I write for as the identity of the third qubit if I consider the terms only with the blue triangle? B cat 1. So we've taken care of the 2 terms that have the blue triangle on top of them. Now let's focus on the terms with 0 1 on Alice's qubits. So this is this term and the term over here. So plus 0 1 tensored with, now what should I write for the third qubit? A cat 1 plus B cat 0. So I've taken care of 4 of the 8 terms. Now let's look at the terms with of this kind, with 1 0 in Alice's position. So I just factorize out the states for Alice's qubits, ket 0 1 crossed with A ket 0 A ket 0 minus B ket 1 plus the remainder the last 2 terms A ket 1 minus B ket 0. So this is the state of the 3 qubit system just before measurement. Just before measurement. Now, is it clear from this 3 qubit state? Is it possible to look at what states does Alice's measurement project the overall state into? If Alice were to do a measurement on her qubits, what would she get? She could get ket 0 0, or she could get 0 1, or she could get 1 0, or she could get 1 1. And what's the probabilities for each of these 4 outcomes? 1 by 4, which is have I missed something? Something, this should be 1 over 2 by the way. What have I missed? One half. Sorry. So Alice's outcomes are zero zero with the probability of 1 by 4, 0 1 with the probability of 1 by 4, 1 0 with the probability of 1 by 4, 1 1 with the probability of 1 by 4. So all of these are Alice's outcomes, possible outcomes, and she's only going to get one of these 4 outputs at a time, and each output will be equiprobable. Each output is going to have a 25% probability. Is that clear? Now nothing happens to Bob's qubit. Alice has now taken her qubits, done some kind of operation, and gotten a pair of bits as the output. So now the quantum state with Alice has gone away. It has dissipated. It's disappeared because now she's done a measurement. The qubits are gone. The photons are gone. Now she gets information. And the information that she acquires is a pair of bits. Not qubits, a pair of bits. This is a classical pair of bits, 0 0 0 1 1 0 1 1. This is a classical information. Now what she would do is she would write down the output that she gets on a piece of paper perhaps, or she makes a phone call to Bob and transmits the output that she gets to Bob over a classical channel, over a phone call or a Wi-Fi signal or a WhatsApp call or a facsimile, anything. But the classical information worth 2 bits is being transmitted to Bob. Bob could be in a different part of the universe. So now this message that comes out in Alice's world, this message, some output 0 1 or 1 0 goes all the way to Bob. So this information has to be transmitted, say through light, through an electromagnetic wave, through a laser pulse, somehow, or a Wi-Fi signal. Somehow it has to go out to Bob. And this is limited by the speed of light because none of these signals can travel faster than light. So now classical communication takes place to Bob. Now what Bob does, Bob has one qubit with him. He doesn't know what the qubit is. He doesn't know the state of that qubit because he hasn't made any measurement on his qubit. He's just preserving his qubit and waiting for a message to arrive from Alice. That's what he's waiting for. As soon as he gets the message, which is one of the 4 possibilities, he's going to make a choice. And the choice that he's going to make is what to do with his qubit, so that his qubit becomes an exact replica of the original qubit that was supposed to be transmitted in the first place. So if you look at the quantum state over here, which is the 3 qubit state, Alice has made a measurement. So when a measurement is made, this superposition collapses. When this superposition collapses, only one of the terms remains, and that depends upon Alice's output. If Alice receives ket 0 0, then only this term is preserved, and when this term is preserved, Bob's qubit has to be in this state because Alice's measurement outcome of 0 0 has collapsed this big superposition into ket 0 0 crossed with A ket 0 plus B ket 1. Now Alice measures her qubits, so these qubits physically go away because they just disappear, the photon is annihilated, but she now has transmitted the answer of her measurement 0 0 to Bob. Now Bob has received this 0 0, he's waiting for a message, the Messiah comes, one of the 4 messages arrives, and he sees, opens up the box, opens up the envelope and sees that it's 0 0 written on his message that Alice has kindly and generously transmitted to him. Now he opens up the envelope and sees a 0 0. Immediately he recognizes that his qubit is already in the state A ket 0 plus B ket 1, which was supposed to be transmitted in the first place. So he does nothing. He does nothing to his qubit, and he will immediately decide and declare that my qubit is in the exact same state as the original qubit, and you can say that with certainty. He's not going to measure it. He doesn't know what the state is, by the way. doesn't know what small a is, he doesn't know what b is, but at least the state is an exact replica of the original quantum state that was supposed to be transmitted. Got it? Now if this were Alice's outcome and Bob receives this message 0 1, and all of this happens with the probability of 25%, now Bob's qubit is going to be in this state. The whole the whole quantum state collapses into ket 0 1 crossed a ket 1 plus b ket 0. And now what would he do in order to recover the original state? What should he do? He should do a what's a mirror? I mean there's no mirror. He should do a quantum NOT gate. He would do a quantum NOT gate on his qubit. So he would apply this gate on his solitary qubit, a quantum NOT gate. What that quantum NOT gate is going to do is going to transform his qubit into the original. All right. So NOT gate in matrix form, by the way, is this, right? This is also called an X gate. X gate. So now Bob, if Bob were to receive the message 0 1, he's already made up his mind that he's already pre-decided that if he receives the message 0 1, he will apply a NOT gate to his qubit. And after the application of the NOT gate, his qubit is going to be in the exact same quantum state as the original qubit. Still, he doesn't know what the original qubit was because he doesn't have any information about A or B, but the qubit is going to be an exact replica of the original qubit. Right? Now what happens in this third case? In the third case, this is his output. So what should Bob do to his qubit? Which gate? Phase gate with a phase of pi. So he will apply a phase gate with a phase of pi, which is also called a Z gate, and its matrix form is 1 0 0 minus 1. That's what Bob is going to apply. He's going to apply local unitary gate, 1 qubit gate on his qubit depending upon the classical information he receives. And what's going to happen in the fourth scenario? Right, or a phase gate followed by a NOT gate. So he will apply a NOT gate, which is an X gate, followed by a Z gate. And this is proportional to 0 minus iota iota 0. This is also called a Y gate. So what's going to happen overall is that based upon this classical information now I'm going to represent by 2 arrows because it's classical, and I'm going to put a big arrow on it. This is classical information that occurs over a classical channel. Classical channel like an optical fiber or free space communication or anything, Wi-Fi or a piece of paper or a Dakia, anything. These are quantum wires, quantum bits move on these wires, but this is classical information. Now this classical information is transmitted to Bob, and depending upon the message that Bob receives, Bob is going to apply some gate. Bob applies some gate, single qubit gate to his qubit, and lo and behold, his qubit after this transformation is going to be an exact replica of the original qubit, which is what I've written over here. Now I would like to ask a few questions. Let me first ask the questions. Number 1, does this violate quantum cloning? Why does it not violate quantum cloning? Yes, please. The first qubit has been destroyed because it has been measured. Cloning means that you keep the first qubit and transfer its state to another qubit, and you keep 2 copies. So that's what copying means. Here, one of the qubits is destroyed. The second question is, does this happen faster than light? No. There is no superluminal communication. The speed of light c is the ultimate limit at which information can transfer. This is a postulate of special relativity. So no communication faster than light happens here. So it's a slow process, which means the speed of light is the upper limit. The third question I would like to ask is, a qubit is being transferred, but a qubit is not physically being transferred. The matter is not going from Alice to Bob. Only information is going from Alice to Bob. Even though we started off with an entangled pair and one qubit went to Alice, the other qubit went to Bob, and Bob might have gone far away, carried the piece of matter with him, but eventually Alice is not sending the qubit, the physical qubit that carries the quantum information. It's not being physically transmitted over a channel to Bob. Bob is just receiving information. This means information is physical itself. Information has a physical value. It can be measured, it can be quantified, and that's the whole kind of claim of Shannon's theory of information. The information is physical, and that's how quantum computers kind of came into being, because they were treating information physically. No matter is being transported. No matter transport. By the way, when we talk about science fiction, so this is a popular theme in science fiction. In science fiction, what teleportation is generally represented as is that there is one person standing at one point in time at one planet, Earth, and a neighboring exoplanet in another solar system. This, if I am being teleported, I just fizzle away and immediately I am transferred at another location, and my matter does not go all the way from Earth to the exoplanet. It just reappears at the exoplanet instantaneously without transferring through the entire medium. But this is just popular excitement level stuff. This doesn't really happen. Teleportation, as you've seen, with all its mechanics, with all its beauties, this is how teleportation unfolds. And this is done experimentally. Teleportation can be done over now hundreds of kilometers. Quantum states can be transported hundreds of kilometers across. And the transport of quantum state is actually, this implies transfer of quantum information. Bob now has a qubit which is an exact replica of the original qubit that Alice had. And what's making this happen? What is the kind of secret ingredient here? It's entanglement. So the secret ingredient in this puzzle is entanglement. Entanglement is being used as a resource. There is correlation here between the second and the third qubit. Now this correlation carries over all the way, even though Alice and Bob are separated in space, separated in time. It carries all the way. And you do a measurement on a subsystem of the entangled system, it immediately determines what you get on the third qubit, because this is entangled with one of the wires in the pair that Alice possesses. So entanglement is the resource, and by transferring two classical bits, one qubit can be transferred. And this is really, really beautiful, because let me tell you why. So now this teleportation is using 2 bits of classical information plus one entangled pair to kind of achieve the transfer of one qubit. Now why is this so beautiful? Now when you read physics, especially modern physics, if you're not beleaguered by GPA, and if you're not under the kind of stress and impositions of midterm exams and final exams, you really appreciate the beauty of this. Now what's happening here is something astounding. I really find it interesting, because just with the transfer of two classical bits, these are just 4 kinds of strings, 0, 0, 0, 1, 1, 0, 1, 1. These are just of 4 kinds, one of 4 kinds. But the quantum state is richer. Why is it richer? Because A and B are complex coefficients, and they could be anything. They could be really anything. A could be any number. B could be any complex number, until and unless their normalization condition is preserved. So generally qubits are represented by, we've seen that the qubits can be represented by kets. We've seen that qubits can be represented by vectors, column vectors. A third graphical way of representing a single qubit is by drawing a sphere. Now this sphere is a kind of 2-dimensional object, but it's spherical, and all the quantum states in this abstract notion live on this sphere. Everything lives on a sphere. Now on the north pole lives the quantum state ket 0. On the south pole of this sphere lives the quantum state ket 1. And superpositions like, so if I were to draw the equatorial plane, so this is the equatorial plane, and if I look at the x axis of this equatorial plane, so pointing towards you on this sphere is the state which is a superposition of 0 and 1. So this is ket 0 plus 1 over under root 2. Here on the kind of east side, the cardinal point, lives the state ket 0 plus iota ket 1 over under root 2. I go back to the sphere. At the back side lives ket 0 minus ket 1 over under root 2. Here lives ket 0 minus iota ket 1 over under root 2. But the quantum state can actually live anywhere on this sphere. It can be anywhere on the sphere. So how many states can exist in this 2-dimensional system? An infinite number of states. So this quantum state, which is being transported psi equals A ket 0 plus B ket 1, can live anywhere on this state, on the northern hemisphere, southern hemisphere, equator, close to the north pole, south pole, anywhere on the sphere. So this sphere has an infinite number of points on it, and it's a unit sphere just radius. You can't go inside the sphere, but you can always remain on the infinite variety of points that exist on the sphere. By the way, this is a mathematical representation. The qubit doesn't look like this. It's not a diagram of the qubit. It's a representation of the qubit which is classical and which only works for a single qubit. So look at the richness here. Just by using 2 classical bits of information, you can kind of teleport and transmute and reproduce this accurately pointing state on the block sphere, which has an infinite number of varieties and possibilities. You can do it accurately just with 2 classical bits and an entangled pair. That's the beauty of it. And last point I would like to make in conjunction with teleportation is the following. Well, if Bob doesn't receive any message from Alice, if Bob lives in Shab-e Hijra waiting for a message from Alice and never gets it, what would his state look like? What would be the ket for Bob? Bell state? It's 1 qubit, can't be Bell state. Nothing? So what will his qubit look like? I mean, it must have a state description, still a state. But Bob hasn't received any message from Alice because either the message has been interrupted and intercepted by an eavesdropper. You're getting close.
It exists in all states.
You're getting close.
Would it be a superposition of the 4 states? The second qubit, the third one?
Not really. It's it's really going to be a totally random state. I can't write this as a ket because it's not a pure state any longer. It's not a ket any longer, but it's a totally random state. Totally random. So now Bob, if Bob doesn't receive any message from Alice, Bob's qubit could be anything. Either Alice hasn't made the measurement and Bob is trying to be he's trying to do it really fast, but Alice is not kind of responding, she hasn't done a measurement. The other possibility is Alice's message gets lost in the atmosphere or hijacked by an eavesdropper. Or it's just that Alice decides to part ways with Bob and she doesn't really send him a message. In that case, Alice's qubit is totally random. He knows nothing about his qubit. It could be anywhere on this sphere. So this lack of information is randomness. All of a sudden, just two bits arrive, two classical bits arrive, two enigmatic numbers, zeros and ones, two of those bits arrive, and all of a sudden it's a eureka moment and Bob does a transformation to his qubit and immediately can declare safely with certainty that his qubit is going to be an exact replica of the original qubit, though he doesn't know what the state is. By the way, since you can't clone states, you cannot also measure quantum states precisely, by the way. I can take a question.
Sir, my question was, is the block sphere an example of a vector space?
Well, block sphere represents a two-dimensional vector space, Hilbert space.
How are we able to traverse the lateral dimensions and
So it's just the surface of the sphere that we are interested in. That's the quantum physics that we learn at this level. Otherwise, it's a mixed state. You go inside the sphere. Any more question about? Yes, please.
Sir, how does Bob know that ket 0, 0 corresponds to ket A ket 0 plus B ket 1?
So Alice and Bob have already decided this. They already know what kind of entangled state comes in. What are the four kinds of Bell states? They already know what Bell state that has been produced. So they've already decided that. Now, one thing I would like you to do what was the last point? The last point was about the randomness. Bob's qubit is intrinsically random until Alice makes a measurement. One question I would like to ask you. If Alice makes a measurement and doesn't tell the result to Bob, she kind of withholds that piece of information, will Bob's qubit be a random state? No. It would be projected into the one of the four possibilities. But those one of the four possibilities will only be the original state with 25% probability. It could be the other three as well. So Bob's qubit will now be definite. It will no longer be a random state, but Bob wouldn't know whether his qubit is an exact replica of the original. He would need to get that information from Alice in order to do something to his qubit so that it becomes an exact replica of the original. All right, now, by the way, one thing which is really a homework problem, and I might ask this in a quiz, like next Thursday, is any question about teleportation, by the way? Yes, please. Sorry? ये मैं आपको इसकी ये वाली let me give the excuse me, the question is, right, your friend has asked a question. So if this is the message that Bob receives 1 0, it corresponds to this quantum state. Now this should be plus sign here. So how do you get a plus sign? You do a phase operation, which means you apply this gate. So you'll get a plus sign here. That's it. Yes, please.
Sir, if the whole of the experiment would be like made otherwise, the Bob had made the measurement, like Alice had to, how would that work?
Teleportation doesn't work that way. It's not going to be teleportation any longer. So one thing I would like you to do as a homework problem is this entanglement swapping. Entanglement swapping is if I have two pairs of entangled qubits. The first two qubits are entangled with one another, say the Bell state phi plus, an entangled state, and the third and the fourth qubits are entangled with respect to one another. So now we have a 4 qubit system.
A cat 0 plus B cat 1.
So Alice and Bob have already decided this. They already know what kind of entangled state comes in. What are the 4 kinds of Bell states? They already know what Bell state that has been produced. So they've already decided that. Now, one thing I would like you to do so what was the last point? The last point was about the randomness. Bob's qubit is intrinsically random until Alice makes a measurement. One question I would like to ask you. If Alice makes a measurement and doesn't tell the result to Bob, she kind of withholds that piece of information, will Bob's qubit be a random state? No. It would be projected into the one of the 4 possibilities. But those one of the 4 possibilities will only be the original state with 25% probability. It could be the other 3 as well. So Bob's qubit will now be definite. It will no longer be a random state, but Bob wouldn't know whether his qubit is an exact replica of the original. He would need to get that information from Alice in order to do something to his qubit so that it becomes an exact replica of the original. All right, now by the way, one thing which is really a homework problem, and I might ask this in a quiz, like next Thursday, is any question about teleportation, by the way? Yes, please. Sorry? ये मैं आपको इसकी ये वाली, let me give the, excuse me, the question is, right, your friend has asked a question. So if this is the message that Bob receives 1 0, it corresponds to this quantum state. Now this should be plus sign here. So how do you get a plus sign? You do a phase operation, which means you apply this gate. So you'll get a plus sign here. That's it. Yes, please.
Sir, if the whole of the experiment would be like made otherwise, the Bob had made the measurement, like Alice had to, how would that work?
Teleportation doesn't work that way. It's not going to be teleportation any longer. So one thing I would like you to do as a homework problem is this entanglement swapping. Entanglement swapping is if I have two pairs of entangled qubits, the first two qubits are entangled with one another, say the Bell state phi plus, an entangled state, and the third and the fourth qubits are entangled with respect to one another. So now we have a 4 qubit system. All right. Now what happens is the last concept which I would like to just kind of highlight in this module of the course, which is the last part of the first module, is about non-locality. We've already seen non-locality when we talk about entangled states. So when we address non-locality, when we talked about entanglement, entanglement really means that the two possessors of an entangled pair, they can be in different parts of the universe, far apart. If a measurement is done on one party inside the entangled pair, it automatically, you can deduce what's going to happen to the second party. That's not an entirely non-local effect, and still it's a no signaling effect, which means nothing is traveling faster than the speed of light. So I just want to highlight this in a kind of contextualized game. So the game that I would like to play is called a game of non-local boxes. Non-local boxes. So this, by the way, you won't be able to find in any of the resources that I've uploaded, and I've uploaded some very good resources. You should go and look them up, especially the book 6 Quantum Pieces, which I only discovered recently, but it's very closely related to the contents that I'm covering in this course. So what is a non-local box? Suppose I have two boxes. They could be close together, far apart, anywhere in the universe, and each box takes in an input. Say the first box takes in an input A and gives an output X. A is a bit, X is also a bit. Do you know what a bit is? 0 or 1, right? Likewise, so this is with Alice, this is with Bob. Thank you. So Bob's non-local box also takes in a bit, 0 or 1, let's call it B, and churns out an output Y. Now Alice and Bob play a game very similar to the zero kata game that you play. Now the game is designed such that Alice and Bob decide that they want to play a game in a manner that they would like, both of them would like to win. The game needs to succeed. And what is the criterion of success? The criterion of success is that X multiplied with Y equals A exclusive OR with B. All right. Now let me on the sidelines remind you what an exclusive OR is. An exclusive OR of 0 with itself is 0. Exclusive OR of 0 with 1 is 1. 1 with 0 is 1. And 1 with 1 is 0. That's how we define an exclusive OR. So now if they kind of want to play this game and want to maximize the probability of success, they need to make up a decision, as Alice and Bob need to agree upon something. So what they want to agree upon is that if Alice says if I get this A as an input, I will give out this X, and Bob tells Alice that if I get this B as an input, I will give out this particular output, and they cannot change the rules of the game in between. They have to be consistent. That's the kind of rule of the game. So now what kind of recipes can they come up with? Let's see, can they always win? Can both of them always win, or will the game always succeed? So I want to use a notation that I'm familiar with, but it doesn't really matter, but okay. So X is the input to Alice's Bob, Y is the input to Bob's box, A is Alice's output, and B is Bob's output. This is the rule of the game. X and Y are the inputs, and A and B are the outputs. And this is what you want to happen in most of the cases. So now let's construct a truth table. X and Y are the inputs, so these are my inputs, and A and B are my outputs. So what are the possible, yes please. Yes. So what are the 4 possible inputs to this 2-box game? 0, 0, 1, 1, 0, 1, 1. So X could be 0, Y could be 0. X could be 0, Y could be 1. X could be 1, Y could be 0, Y could be 1. So these are all the 4 possible inputs that can go into the 2 boxes. This box takes X as an input, Bob's box takes Y as an input. Now Alice and Bob need to decide what A or B should they produce for a particular X and Y. So Alice says that if I were to get 0, I'm going to output a 0. Now how should Bob respond? Bob wants the game to succeed, so he said, okay, if you give 0 as an output with your input 0, I will also give 0. So the game succeeds. So if X is 0 for Alice, the output is A, I need to put a 0 here as well, because Alice cannot change the rules of the game. If she gets a 0, she always outputs a 0. And if Bob gets a 0 as an input, outputs 0, there should also be a 0 here. Now if you look at the second row, Bob needs to decide what to put in here. So Bob must put in a 0 here if he wants the game to succeed, because then A exclusive or B would be 0, which is equal to the product of 0 and 1. Right? So if this is 0, then this must be 0. Now if this were the case, if Alice decides that if I get 1 as an input, I'm going to produce a 1 as an output, but then this will fail, but this will succeed. So the first row is going to succeed, the second row is going to succeed, but the third row is going to fail, and the fourth row is going to succeed. So that's one way of constructing this truth table. It's not possible to have all 4 rows win at the same time. That's not possible. Yes?
Sir, I'm sorry, can you explain कि जो exclusive और वाली बात की थी वो, and by what exact criteria are you saying कि ये succeed हुआ है?
So this is the criterion for success. What does this mean? This means, I really need to get this microphone sorted out. Sorry. What this means is X and Y, their product must equal the exclusive OR of A and B. So these are all the possible values of the inputs X and Y, and Alice and Bob decide their A's and B's one by one for each row, and they want to maximize the chances to win. They cannot design a truth table in which you get success in all 4 rows. You'll always get a failure in one of the 4 rows. Let's try a different combination. X, Y, A, B. The inputs are still the same. Now let's start from the bottom up. So if X and Y are both 1, if you want this game to succeed over here, then what you would need to do is, let's actually start with the 3rd row. If you want the game to succeed, you want a 0 here. So let's put 1, A and B equals 1, because the exclusive OR of 1 with 1 is 0, and the product of 1 and 0 is also 0. Yes, please. You just make your first choice. So I'm looking at different combinations, possibilities of this table. You can start off with anything. Now if this were the case, if X were 1, A is 1, if Y were 0, B is 1, so Y is 0 here as well, so this must be 1. So if I were to make this game succeed over here, this has to be 0. This must also be 0 then. Now I can put 1 here and a 1 here. So what's going to happen is that this is success, this is success, this is success, but this is, oh, second one is fail. This is fail and this is success. Still 3 out of 4 times I will make this game work. So the probability of success is going to be 3 by 4. I cannot win this game classically by more than 75%. That's my ultimate rate of success. I cannot do better than this. Now these boxes can be really, really far apart. Now what quantum mechanics allows you to do is that it allows you to beat this probability. It allows you to do better than this. Now this was the problem when Einstein, Podolsky and Rosen in 1935 first presented the idea of entanglement. This is what confused them. They thought that entanglement cannot be true. It's not possible that you have action at a distance. You do something with Alice's qubit and something happens to Bob's qubit without any interaction, without any communication. So there must be 2 things that are missing in the theory and framework of quantum physics. So how can one bypass or circumvent this limitation that action at a distance is taking place? One possibility is that Alice and Bob somehow communicate with one another. If they're able to communicate with one another, Alice can be super smart and she can do a measurement and do a secret phone call on a hotline. Bob could receive a phone call from Alice, no one else knows about it, and she could secretly whisper her result to Bob, and Bob could in the middle of everything, he could adjust his output and kind of change his transformation states and produce an output which is totally correlated with Alice's. But as you know, this kind of transmission is not possible, because even if these objects were really far apart, and so far apart that it would have taken light billions of years to travel, but still the effect is seen instantaneously. So this kind of outrightly rejects the possibility of any kind of communication between Alice and Bob. So communication is not allowed between Alice and Bob. What Einstein proposed was that there's something hidden here, some other variables, some other ingredient recipes that Alice and Bob know at the time of the creation of the entangled pair, but which is not factored into or does not manifest in the theory of quantum physics. some hidden recipe at the time of the creation of the entangled pair, and that recipe is hidden from us. It's not kind of manifest in the theory of quantum physics, at least for the time being. So we should search for these hidden variables. We should search for these hidden ingredients. These ingredients are called local hidden variables. Now, for many years, for about 3 decades, this was an outstanding question. No one knew how to solve this problem. In 1960s, John Bell came up with this idea of a mathematical inequality, that if that inequality is violated, you cannot have local hidden variables, or quantum physics will be correct and it will be truly non-local. So now all of this seems very philosophical and tongue twisting. So let me kind of show how this unfolds through this example. Now this example sets a limit, a classical limit on the probability of success. That's 75%. Now what we would like to do is we would like to design a quantum game that works according to the rules of quantum physics, employs entanglement, entangled pairs of qubits and kind of measurement basis, and let's try to beat this limit. So this is a kind of an inequality. If you can surpass this threshold, you can say that quantum mechanics is non-local. There can be action at a distance without the need for local hidden variables. That's what I'm trying to aim at. So now let's see how this process unfolds. Suppose I have an entangled pair of qubits. Sorry. Yes.
What does it really mean by being local and
Non-local means that you have two objects that are really far apart. You do something on one party, it immediately affects the output on the other party. That's totally non-local behavior. Local is something that you do at one location. Yes, please.
Would the probability of failure be also 3 by 4?
What's the probability of?
Failure, would that be at the maximum?
Well, you can work this out. It could be greater than 1 by 4. The probability of?
Failure with the maximum?
At the moment, the probability of failure is 1 by 4. That's the maximum. So we're looking at bounds. What's the best you could do with this success criterion? You can of course do worse than this.
No, but I'm saying that is there a possibility that चारों failure कर लें, or would that be also with the same probability of being successful?
Well, quantum physics doesn't talk about that. It talks about whether you can do better than this. Classically, I think you can do worse than this. All right, so now let's talk about Alice. Now Alice has two possible inputs, two possible values of x. X could be 0 and x could be 1. Now Alice decides that if she gets, what happens is, all right, so let me first kind of, this is Bob's box, Alice's box. How many qubits do we have here? 2 qubits, they are entangled. 1 qubit goes to Alice. Say the first qubit goes to Alice. The second qubit goes to Bob. Right? So this has 2 qubits. One goes to Alice, the other goes to Bob. Now what Alice and Bob do is that they measure their qubits. Simple as that. But Alice can measure her qubits in 2 ways, because her input x can be of 2 kinds. This input x could be 0 or 1. So she could measure her qubit that she receives from the entangled pair in 2 distinct ways. So there is some switch here, some kind of maybe a supernatural being or a natural being or an observer or an experimenter who has a switch or a coin tosser. Now that coin tosser tosses the coin and you get a 0 or 1 with equal probability, and depending upon what output you get, Alice does a measurement in a particular basis. So if Alice receives a 0 for her classical switch for the input, she measures in the horizontal vertical basis. Suppose we're talking about photons. So just to simplify things, so this is HH plus VB. Simple. So if she gets 0 as her input, she measures along the horizontal vertical basis. How would she do that with photons? She would use a polarizing beam splitter that has two outputs, one corresponding to ket H, the other corresponding to ket V, and she's going to see which of the detectors is going to click. All right. Now if she receives 1 as her input, now these are classical numbers, these are just classical switches, 0 and 1, or this is a red light, this is a green light, there's some blind person who's actually operating these lights and they're shuffled together. Sometimes he presses light, red comes out. Alice sees the light, red, she chooses her measurement orientation H and V. If she sees a blue light coming out, she changes her measurement orientation and measures along ket D and A. And I would like to remind you that ket D is 1 over under root 2 ket H plus ket V, and ket A is 1 over under root 2 ket H minus ket V. All right. Now she gets an output. When she measures her qubit, she gets her qubit either, if she were to measure in this basis, she would get ket H or ket V as an output. Suppose if she gets ket H, her output is 0, this corresponds to 0, this corresponds to 1. So she outputs a classical bit, because Alice, as you know, has to output a classical bit. So she outputs ket 0 or 1 depending upon whether the photon collapses onto the ket H state or the ket V state. And if she were to measure in this basis, in the diagonal anti-diagonal basis, she would output a classical bit 0 if the measurement is along ket D, and she will output 1 if the measurement is along the anti-diagonal axis. Is this clear? So I'm going to explain this in a bit more detail, but don't worry. So now what's going to happen is that Bob also has two possible inputs, 0 or 1. Now Bob also chooses between two bases, two measurement orientations. One of these orientations is kind of, let me draw this in a kind of bigger fashion. So you don't need to erase this, everything is accurate, but I'm going to draw this in a kind of bigger fashion. So Alice measures in either ket H V basis, or she measures in D A basis. This, as you know, is pi by 4, 45 degrees. So these are two Alice's possible measurements. This is for x equals 0, this is for x equals 1. And this really, in physical terms, this corresponds to a beam splitter PHV that takes in a photon and produces two output channels, one along ket H, one along ket V, and you place detectors after these channels. If this detector clicks, she outputs a 0, and if this detector clicks, she outputs a 1. She also has to give an output A. So this corresponds to the output 0, this corresponds to the output 1. Likewise, this corresponds to the output 0, this corresponds to the output 1. So what's the difference between these measurements is the value of x. The value of x determines what orientation is she going to make a measurement in. Yes, please.
So if I'm getting this right, so Alice knows, okay, I've got x1 or I've got x0. Based on that, she'll either put her qubit into a VHV polarizer, analyzer, or she'll put it, if she gets x1, she'll put it into an AD.
Exactly. So she's going to change the style of her measurement. First of all, she's going to make a measurement like this, then she's going to make a measurement like this. That's it. She's going to change her orientation of the measurement. All right? So you can project onto any quantum state. Your basis could be anything. You don't need to measure along H or V. You could measure along any axis. So I'm going to give you an example for that. Just hold on slightly. So Bob also has two bases to his disposal. Two kind of measurement orientations. One corresponds to y equals 0. The other corresponds to y equals 1. By the way, this is the simplest example I can think of for a Bell's test. So other tests are more complicated, so you'll have to bear with this. Even though it's simple, it might look a bit cumbersome. It's not hard, it's a bit cumbersome, that's it. Just looks tedious. So for y equals 0, Bob's orientation is kind of get alpha, and alpha, let's call it alpha perpendicular. Now this alpha is at an angle of 22.5 degrees, which is pi by 8. So horizontal vertical is like this, diagonal anti-diagonal is like this. Alpha is slightly tilted at 22.5 degrees with respect to the horizontal. So if I were to write the state ket alpha in terms of ket H and ket V, what is it going to look like? Can I express ket alpha as a superposition of ket H and ket V? Yes. What would that prescription look like? Cosine of shabash. Aage? Excellent, that's beautiful. And what about alpha perpendicular? Negative where? Negative sign सॉरी लिखाई बिल्कुल ही खराब होगी. All right, so this is ket alpha, this is alpha perpendicular, and you can work this out. I mean, this is the vertical axis, this angle is 90 degrees plus alpha, so you get cosine of 90 degrees plus 22.5, which is minus sine of 22.5. That's it. So you can construct these states. Likewise, for y equals 1, Bob orients his axis so that they tilt 22.5 degrees below the horizontal. So the new configuration for y equals 1 looks like this. 22.5 degrees below the horizontal axis. So let's call this state ket B. Let's call this B perpendicular. And I can also write down what these states look like in terms of ket H and V. So ket B is going to look like cosine of pi by 8 ket H minus sine of pi by 8 ket V, and B perpendicular is going to look like, I think, sine pi by 8 ket H, I think, plus All right. So this is how Alice and Bob decide to play the game. Let me recap. An entangled pair of qubits is produced. It's in a Bell state. One of the qubit goes to Alice, the other qubit goes to Bob. Now Alice's box has two possible inputs coming from a random process like a coin toss 0 and 1, and depending upon what she sees on her coin, a 0 or a 1, a head or a tail, she decides to measure her own qubit in a particular basis. And those bases are of two kinds. One is the horizontal vertical basis, the other is the diagonal anti-diagonal basis. Likewise, Bob makes up his mind to use two different kinds of measurement bases. One of them is the alpha perpendicular basis, and this is how we define this. The other is the beta perpendicular basis, and this is how we define it. Now if the output in Bob's case, if this detector clicks, now there are two detectors placed at the two kinds of outputs, right? So if this detector clicks, Bob calls this 0 and calls this a 1 if this detector clicks. If this detector clicks, Bob calls this a 0 and calls this a 1. It's very simple. So there is consistency. Alice and Bob, each of them have to output a bit, right? A 0 or a 1. They must have an A and a B. That's how they decide on churning out the outputs. Now let's play this game quantum mechanically. We've generated quantum entangled states, given one to Alice, given one to Bob, and they choose their measurement basis depending upon X and Y, and we want to see what they get. Now on a big piece of paper or blackboard, so let's use this part. It's a very nice calculation, by the way, and a very interesting phenomenon will be observable. So all right, yes please. Can you speak up?
So can you explain how we got the state get beta and get beta, the perpendicular get beta? Like how we reach those bits.
So ye wala?
Yes.
So if this angle is pi by 8 but below the horizontal axis, so the projection on cat H is going to be cosine of pi by 8. This is cat H, cat V. It's pi by 8. So projection along H is cosine pi by 8, and the projection along V is so this projection of this state on this,
सर वो नीचे नेगेटिव y के अंदर नहीं होगी.
ये एंगल कितना है पाई बाई 8. तो what am I missing here? So this is so what's this angle? 90 minus this is pi by 8. So this is all right. So what is this angle overall? This angle 90 plus pi by 8. So cosine of pi by 2 plus pi by 8. What's this? Minus sine of pi by 8. This is this term. Okay. Likewise, you can find out what's going to happen to this particular B prime. Okay. This is Bob's. This is Bob's measurement basis.
So how does Alice get her measurement from this?
अभी पूरी बात हो लेने दो. So what are the possible values of x and y? Yes, please.
So what is the role of this entangled state?
Well, come on, I'm going to explain this. So what are the possible values of x and y? 0, 0, 0, 1, 1, 0. So I get 0, 0, 0, 1, 1, 0, 1, 1. Now what are the possible values of a and b for each of these 4 states? Could be 0, 0 here, 0, 1, 1, 0, 1, 1. What about this? 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. All right. So now which of these kind of entries gives you a success for the game? Does the first row give you a success? Yes. Does this second row give you a success? No. This doesn't give success. Does this give success? Yes. Success? No. Success? पहले वाला success है. So the product is 0, so this gives you success. What about this one? No. Success? What about this term? Yes. Success? Yes. Now what about this term? 1 into 1 is 1. 0 plus 0 is 0. Failure. 0 plus 1 is 1. Success, success, failure. So how many times are you going to win? Half the time. But this seems to be worse than the classical scenario. So instead of I promise that we can do better than the classical scenario, this seems to be worse. But what's the catch here? So I'm losing half of the time and I'm winning half of the time. The success probability looks like 50%. But there's a catch. It's actually greater than 75%. How can I prove that? How can I prove this? The success is actually greater than 75%. नहीं कोई टेलर सीरीज नहीं है. What about all these basis business? We have to compute the probabilities for each of these outcomes. And then we need to add up all of the probabilities. So let's calculate, for example, the probability of this outcome. We only care about the successes. The failures we don't care about because we want to find the probability of success. So let's calculate the probability of this outcome given these inputs. So now x and y are defining the basis, the measurement basis, and these are defining the outputs. So the probability of Alice getting a 0 and Bob getting a 0, given that x were 0 and y were 0. So now this defines what basis Alice has made a measurement in and what basis Bob has made a measurement is. And what's the input quantum state? It's the entangled state. So how do we calculate probabilities? We take the quantum state, in this case phi plus, and we find the projection onto the relevant measurement axis. So A equals 0, this is A, this is B. A equals 0 with x equals 0 corresponds to this outcome, doesn't it? X equals 0 is horizontal vertical measurement orientation. Output 0 corresponds to the horizontal detector. So Alice gets an output, a click on her horizontal detector. Therefore, you take the bra H, which represents the projection on to the horizontal axis for Alice. Now let's look at Bob. Bob gets an output 0 corresponding to a basis that corresponds to y equals 0, which is this basis here. So which detector is clicking? It's this alpha detector that is clicking. So now you take the tensor product with alpha, and then at the end take the modulus square of this. So let's see what this looks like. This is H alpha, Alice's qubit, Bob's qubit. You take the inner product with the entangled state, the EPR Bell pair. So 1 over under root 2, the input state were H plus V. Now if I were to take the inner product, which means that looking at this dual bra, this ket, take the inner product, will it be 0 or non-zero? Non-zero. What about the inner product of this with this? 0. So I only need to consider this inner product here. So this would be 1 over under root 2. I just combine the first qubit with the first qubit and the second with the second qubit, bra H, ket H for Alice, bra alpha and ket H for Bob. So this turns out to be 1. So I'm left with 1 over under root 2, the inner product of alpha with H. Now alpha is defined in this fashion. So the inner product with H will be cosine of pi by 8. So this will be cosine of pi by 8. Then I take the modulus square of this. So I'll get this probability. This probability is going to be 1/2 cosine square pi by 8. Then I calculate this probability. It's also going to be 1/2 cosine square pi by 8. You can do it for yourself, the homework problem. This probability is also going to be 1/2 cosine square pi by 8. 1/2 cosine square pi by 8. So all the top 4 values, each one of them has a probability 1/2 cosine square pi by 8. Now let's look at another term. Let's look now at possibly this term, right? You want to look at this term? Let's do a similar calculation for one of the terms at the bottom. Let's look at this success term. Let's calculate the probability for this term. So let's first calculate the inner products. Excuse me, the inner product of phi plus. Now let's be careful here. What basis is Alice measuring in? In the diagonal anti-diagonal basis. And what is she getting? An output 0. So this corresponds to ket T, because x equals 1 and she's getting 0 as an output. So it corresponds to projection on the ket D axis. This detector is going to click. So you need to write ket D here, tensored with. Now let's look at what Bob is getting. Bob is getting 1 as an output, with 1 the measurement basis being the kind of beta prime. So but he's getting a 1. What does that correspond to? The measurement basis is this one and the output is 1. So it corresponds to projection on this axis, which means this detector clicks. So this would be B perpendicular. Then I can take the modulus square of this. So this turns out to be, now bra D is H plus V. This is the first qubit crossed with B perpendicular. We need to write down the bra corresponding to this. This is going to be sine of pi by 8 bra H plus cosine of pi by 8 bra V, and then I need to write the entangled state 1 over under root 2 H plus VV. And then I take the modulus square of this. Now I can just expand the bra part. So this is 1 half. I take this out of the modulus square, I get 1 by 4. This is sine pi by 8 HH. So sine pi by 8 carries over. So I am left with sine pi by 8 plus this term with this terms give me ket bra VV, and this combines with this term, but the coefficient here is cosine pi by 8. So I am left with cosine pi by 8. This is my probability. It's not 1. It's 1 by 4, 1 plus नहीं 1 नहीं आएगा, sin square pi by 8 plus cosine square pi by 8, which is this, plus 2 times. So I'm left with 2 times so I'm left with 1 over 4, 1 plus now I can calculate this probability. This probability, by the way, is going to be the same as the one I've calculated. I can calculate this probability, which is also going to be the same. This probability is also going to be the same. So I get 4 times this, and I get 4 times this, and I add up all of these probabilities. The answer is about 85%. So if I were to draw a line from 0 to 0.75, this is the classical world, this is the local world, beyond 0.75 up till about 0.85, this is the non-local world. This is the world in which there is non-locality. There is correlations between two distant parties, not explainable by local hidden variables, not explainable by classical communication. And this is, at the moment, the state of the art in physics is, this is how much non-local you can be. You can't have non-locality beyond it in most cases. Sometimes you can. That's called a post-quantum world. So non-locality is the regime of quantum physics. This is where physics really becomes non-local. And in non-local physics, you do something at one point in space, it immediately affects what happens at another location. So your second quiz is going to be on next Thursday. Homework number 2 has been uploaded, and 2 weeks from now, inshallah, you're going to have your midterm.